Hello everyone, welcome to Storage Developer Conference. This conference was supposed to happen in May, but because of the pandemic, we are having it in December. Hope everyone is safe. Please stay safe. Hi, my name is Ravi Kiran Gummaluri. I work for Micron Technologies in 3D Crosspoint Group. Today I am here to explain about memory and storage solutions with persistent memory and CXL. So the brief agenda is today I'll talk about the problems that today we are facing with scaling the compute, memory, and storage models, and the necessity of a byte addressable persistent memory. There is a need for new interconnects. I'll talk about what is the need for the new interconnects, and we'll briefly talk about the CXL cache coherent interconnect CXL. I'll give a brief introduction of the CXL, and we'll talk about the CXL different protocols and device models. And in the last, we'll talk about the use cases with CXL plus persistent memory. Let's talk about some of the problems that we have today with the scaling the compute, memory, and storage models. So we know the Moore's law states that number of transistors in a given IC will be doubled every 2 years and the cost will be half. This holds good till last decade. And in this current decade, we do see the decline in Moore's law. Recently, the many chip vendors are trying to explain the different problems that they are facing with 7 nanometer node. That explains us the decline in Moore's law. And the vendors are going for different chip packaging technologies, computer architectures, interconnects, and memory models to scale the increased compute requirements. So today, for the increased compute models, we are using GPUs, FPGAs, or hardware accelerators in order to compute. Increased compute can be half-loaded to these accelerators, and we are working on the increased workloads. So even though there is a decline in Moore's law, the scaling of this compute has been, today we are doing over the GPUs or FPGAs or hardware accelerators. The compute loads have been half-loaded and we are accelerating the designs. Let's have a look close into the memory model. Today, the DDRs are also expanding with the memory, the CPU models. The processor speed is increasing every 2 years, and the memory capacity also has been doubling every 2 years. The problem comes when we have a memory latency. The memory latency is improving only 1.1 times every 2 years. That is around 50% when we compare with CPU performance. The CPU performance is increasing every 2 years, but the memory latency is improving only 1.1 times every 2 years. So there is a gap between the CPU performance and the memory performance. That gap has been filled today by some of our caches. This gap is being handled by our caches today. So for increased performance, we are using a low latency caches in between the memory and the CPU, and we are handling the latency gap between the CPU performance and memory performance. This today we call it as a memory gap, and it will be scaled when the CPU performance is scaling, the memory performance cannot be scaled, and the cache size we are increasing with multiple cache levels. So this is one of the problems that to scale the memory problems. Let's talk about some of the storage models that we have today. The storage models are used to store the data for a persistent model. So you have a DDR in which it's a load store memory, and it's a volatile memory. So in order for a non-volatile memory, we are using the storage devices. The storage devices are slow when compared with the main memory. So the latencies will be more when we are accessing a storage device. And in order to access a storage device, we have n number of software stacks that has to be application before it issues a storage read or write. It has to go through a lot of memory storage layers, and it has to land into the memory device. The media latency also matters here when we talk about the storage devices. The storage device media latency plus the software stack overheads actually kills the performance when we access the storage media. But this is required for our today's memory models because the memory which is there inside our DDR or the host memory is non-volatile. I mean, it's not a volatile memory. If you want a non-volatile memory, you have to have a storage devices which are slow when compared with the main memory, and they have a huge capacity. The main memory cannot be expanded as scalable, but the capacity of the secondary storage devices is huge. But you have a latency. The latency will kill the performance basically. So we have talked about the hardware media latency plus the software stack overheads when we have a storage model today. So there is a lot of gap when we talk between our DDR memory solutions and SSD storage solutions. The DDRs are at a latency of 80 to 100 nanoseconds, and the secondary storage devices are at the latency of 110 to 100 microseconds. So there is a huge gap in the latency requirements. And when we see that we cannot scale the DDR for the capacity reasons because we have limited DIMMs, and the DDRs cannot be scaled as such for a huge capacity, and DDR is costly. So in a pyramid model, if you see, the DDR is fitting with cache line granularity, load store access, and it is volatile. For persistence reasons and for huge capacity, we are using SSDs today. For non-volatile storage and for persistence, we are using it for huge capacity, storage capacity. But the problem is the NAND storage today, what we have NAND SSDs are all block granularity. They're not cache line granularity. So there is a need, and the persistent memory really fits into this model where the persistent memory is a non-volatile storage. It is a load store like a DDR, and it works on a cache line granularity. It has a huge capacity like a SSD and low latency like a RAM. So this fits into a model where you have a DDR having a problem with the capacity, but high latency, but better latency numbers. The storage has huge capacity, but latency numbers are worse there. So persistent memory perfectly fits into this model where it is load store, huge capacity, low latency. This will evolve over in years with the different memory models. Existing models using the DDR and secondary storage or the SSDs for a different model. Now the persistent memory will make sure that it will evolve a new kind of memory paradigm into the system. We were talking about scaling the compute, and we were talking about GPUs, FPGAs, or accelerators today are the first class citizens, that kind of a first class citizens. We are trying to use them for our scaling the compute requirements. But these accelerators are actually working on a given workload. The CPU applications offload some of the work from their host application space to your accelerator. The data will be moved from your host memory to accelerator memory, and the accelerator actually works on that workload and then computes on that given memory and puts that into the local memory of the accelerator and return back this computed memory back to the host. So today in our world, we are using accelerators for accelerating some work, and we are giving the application is offloading some work to the accelerator. Accelerator fetches the data from the host, computes it locally, stores it locally, and return back the computed data to the host. So in a given hardware world, these are not looking like a parallel compute processes altogether. And it looks like a sequential. The CPU is instructing the accelerators to work on something, and there is no seamless processing happening here. And we are accelerating some workloads, defined workloads here with the movement of data. So today, most of the accelerators what we have today are sitting on top of PCIe interconnect. So how PCIe interconnect behaves is the memory attached to your accelerator is local memory to the accelerator is not visible to the host. It is look like a device memory, right? And it cannot be a system memory. So the accelerator has to move the data from the host to its local memory for the latency benefit, and it computes on that local memory and stores the computed data onto the local memory and returns back. So there is no view of PCIe device memory inside the host. And the host, when an application offloads some work, there is no cache domain context in this both. The accelerator works independently with a given memory model, and the application works independently. The application, whatever updates done by the application, is not visible to the accelerator, and the accelerator modified changes is not visible to the application model. So the caches are not coherent in the coherent domain. And the PCIe has huge translation layer latencies for the ordered writes and completion. So in a given view, the PCIe cannot scale, the PCI interconnect cannot scale the accelerator as a first-class citizen for compute, because it has to still rely on the host-centric compute. The CPU has to offload some work, and data movement is there. If you take the latency numbers, rather than compute time, the most of the time will be happening on the data movement from the host towards the accelerator and back to the host. This problem arises because the interconnect is not in a coherent, making the accelerator as a first class citizen by having a coherent domain. So if you have a coherent domain, meaning if you have multiple CPUs on the host today, you can offload some of the applications work to another processor, and they have different levels of cache, with last level cache being coherent to each other. So the application one which is sitting inside a CPU, when it modifies, the modified value is seen by the other applications running inside your other CPU core with the Snoop protocols running on the host. Now you're expanding your coherency domain to your accelerators. You offload some work to your accelerator. The cache inside your accelerator is coherent to your host. Basically, you're expanding your coherency domain from your host to your accelerator, and the changes done by your accelerator is visible seamlessly to the application, and changes done by application is visible seamlessly to your accelerator. This makes the first class citizen, the accelerator as first class citizen, to scale the compute. So we have talked about some of the need for a new generation interconnects. The existing PCI world will not make the accelerators as first class citizens because they are not in the same coherency domain. The data has to be moved from host to the accelerator and accelerator to the host once computed. And they don't really work on a real data. It has to be a snapshot of a data. And these accelerators cannot view on a real-time analytics kind of data. So with the new advancements in the coherent interconnects, it is possible to have the accelerators in the coherent domain, and you can have a compute model, expanded compute model, and the data movement will be less because the caches inside your accelerator and host are coherent. You don't really require to move the data from your host memory to the accelerator and accelerated compute on that. Whatever is required, the byte addressable, the host can fetch the data from its memory or local memory, or it can fetch the data from the host memory and compute parallelly. So with the new advancement in the coherent interconnects, the problems today we have with the existing PCI protocol can be overtaken, and then you can have a coherent domain, expand your compute. I'll also talk about how do we expand memory also with this coherent interconnects. So you can, with the new advancement in the coherent interconnects, you can expand your memory, you can expand your compute, you can expand your storage with persistent memory. So we'll talk about this later. So I'll talk about some of the efforts that industry has put in to bring some of the new generation cache coherent interconnects. So OpenCAPI, Zenzi, CXL, and CXL. These are some of the emerging what you call as a coherent cache coherent interconnects, and the most recent one was the CXL. The OpenCAPI is actually developed by OpenCAPI Consortium, and it is backed up by IBM. Most of the Power9 systems have the OpenCAPI interconnect. Zenzi is another model with a different new physical layer and different mechanicals and connectors, and it is backed up by HP. C6 and CXL are built on top of the existing PCIe interface and has implemented the coherency protocols for reduced latencies, and they modified the existing standards of PCI transaction layer. Because they use the physical form factor of the PCI and they modified the transaction and data link layer, it is inheriting some of the properties or the services that PCI has today, and it builds on top of that as snooping protocols for making coherency domain and expansion memory models. For all these standards to be incorporated, the main factor is acceptability of these standards by various CPU vendors. And this support is required because the CPU vendors has to support this interconnect in order to scale your compute, in order to scale your memory. So when we talk about this acceptance of multiple CPU vendors, so the CXL is the latest cache coherent interconnect, where it is accepted by most of the industry's CPU vendors today. When you take a name of Intel, ARM, AMD, IBM, all of them are part of a CXL consortium. So CXL is an open standard bus, cache coherent bus standard, where it's a consortium model where all the people are sitting together to form this open bus standard. So CXL is open standard, and it's derived from, it has its own factors, but it is now an open standard. Let's talk about what is CXL. So as I said earlier, CXL is using the PCIe physical layer, and it modifies the transaction and the data link layers for some of the protocols it has in order to take this cache coherency and benefits. So when I talk about CXL, so first generation of CXL is aligned with the 32 Gbps PCIe Gen 5, and CXL uses some of the existing PCIe services can be also leveraged from the PCIe world. So let's talk about some internals into the CXL. So CXL basically has three types of traffic classes, or you can name it as a protocol. So on the left-hand side, which I was showing up earlier, so the left-hand side, you can see that it uses the PCIe physical layer, and top of that, it has modified the transaction and data link layer to support CXL.cache and CXL.mem protocols. And CXL.io is also used in order to use the existing PCIe data link layer services and all. So in a nutshell, the CXL protocol is divided into three traffic classes called CXL.io, CXL.mem, CXL.cache. The CXL.io is the transactions are of PCIe transaction type. Both your enumeration, discovery, all the PCIe services can be leveraged into the CXL through the CXL.io protocol. CXL.mem is a protocol which allows you to have the memory which is attached to the accelerator can be viewed as a system memory, and you can do a read writes onto the memory attached to an accelerator. So in an expansion memory model, and this CXL.mem will be used in order to access the memory attached to your accelerator. CXL.cache is a protocol where it helps us the cache or the accelerator cache inside the endpoint can be coherent to your host, and you can have same coherency domain worked, and you can have a parallel compute model with CXL.cache. And you don't really require to move the data from the host to an accelerator. The host can just point a pointer to the accelerator, and accelerator can fetch the data from the host memory or from the local memory, and it can start computing on it. So I'll talk about the top level, how the host and the accelerator connects with each other in the host model. As I described, every CXL device must need to have CXL.io. And CXL.io is responsible for discovering your device, your configuration access, register access, interrupts, all the PCI services which are there on today can be leveraged through CXL.io. So as I see the right hand side, all the PCI logic today, what we have can be leveraged from in CXL.io, and an endpoint device can talk to the host and it can get detected, discovered, and you can access the configuration, registers, interrupts, DMA, ATS services. Whatever we have today on the PCI world can be used in CXL.io, and this helps us in discovery and all the CXL device discovery. As I said, CXL.memory is used for the memory flows, the host accessing the device attached memory. CXL.mem will be used. The accesses, the read-write accesses from the CPU or the application can go from the core towards your coherency cache logic that will lead into the read writes of your memory on the accelerator. And coming to the cache model, the accelerator's cache can be coherent to your host caches or the host CPU last level cache, so that when an accelerator updates a value, it is visible seamlessly to the application sitting inside your host. And when application inside your host is modifying some data, that is visible seamlessly to your accelerator. So with CXL.cache, the cache of the host and cache of the accelerator can be in the same coherent domain. So as I said, CXL.io can leverage some of the PCIe Gen 5, PCIe Gen 5 5.0 services like a DMA, interrupts, SRIOE, ACS, ATS, virtualization. So most of the PCIe services can be leveraged with CXL.io. And so today we are using PCIe with NVMe attached, NVMe controllers, and to have a block storage, to control the block storage memory or a storage. So we can leverage some of the NVMe Express features, and then we can work on CXL.io itself. So CXL.mem is the protocol for the host CPU to access the persistent memory or the memory attached to the CXL device, and CXL.cache is used generally for making the accelerators in a coherent domain to scale your compute. So there are three types of devices that we can make from the CXL. So they are named as type 1, type 2, and type 3 devices in CXL. Type 1 devices are basically cache devices where your accelerator is having a cache and that accelerator is in a coherent domain to your host processors. So this will have a protocols like CXL.io for the discovery of the device and CXL.cache for maintaining the accelerator and processor in the same cache domain. So it will be used basically to scale your compute. If you want to have more compute, then you can attach a CXL.cache or CXL type 1 device where you can scale your compute. The type 1 device accelerator can work on the host memory. It can fetch the host memory and it can work parallelly along with your processor. So you can scale your compute with your type 1 device. Type 2 devices are basically the accelerators having a local cache which can make that accelerator coherent to your host, as well as the accelerator's memory is also exposed as a system memory. The memory attached to the accelerators looks like a host memory, expanded host memory. So with this type 2 devices, basically CXL.io protocol is used for detecting your device and using the PCI services. CXL.cache is used to make the accelerator in a coherent domain to the host. CXL.mem is used to make the reads and writes to the accelerator attached memory. So this type 2 device is used to scale your compute and memory. We'll also talk about how we can scale the storage with PMEM. So these type 2 devices can be really used to scale your compute and scale your memory. The type 3 devices are memory expansion devices. Basically, these type 3 devices are if you have a CXL device with memory attached to it with a memory controller, so that memory can be viewed to the host as a memory expansion model. It can build as a NUMA node, it is expanded. You can use that memory as a system memory and you can use the resources there. So this, if you have a persistent memory, you have different models here. We'll talk about this soon, like type 3 devices, what is the advantage and all. These devices basically use CXL.io protocol for detecting the device, enumeration and all. The CXL.mem protocol is used along with CXL.io in order to have the memory read and write access onto the CXL attached memory. Let's deep dive into the rightmost one, which is the CXL expansion memory type 3 device. For more memory, if the system requires more RAM or more system memory, then today we are scaling with DIMMs. So the form factors which today we have are probably we are using DIMMs as expansion. If you want more RAM, you are expanding your RAM with the DIMM form factors. But with having a memory attached with the CXL, there is no strict the form factor problems with the DIMMs can be eliminated with CXL interconnect and the memory expanded over CXL. And with having a memory expanded over CXL, you will have different advantages. One is the form factors. Because it comes with the PCIe physical form factor, the various form factors today which is supported by PCIe for different storage or memory devices can be leveraged with CXL. And you can use the CXL.io for discovery and all the existing stuff. You can configure the memory controller through the bar access registers like a PCIe driver. And you can have a DMA engine to move a chunk of data from your memory attached to the CXL to the processor domain, right? So the DMA engine can also be programmed. The memory buffers can be programmed. So no longer you have problems with the DIMM form factor, and you cannot have a DMA engines inside your DIMM form factors. So the advantage of expanding memory over CXL is you can have a huge memory. I'll talk about that, how we can have a huge memory. The memory attached to a CXL device, you can have a DMA engines attached to it to move a large chunk of data from here and there. And you can have a CXL.io leverages the PCIe, so you can have a virtualization and all the other services provided by today by the PCIe can also leveraged by the CXL. And you're no longer restricted with some of the problems that we face with the DIMM with electrical and power factors today. So there's the similar thing that we are talking about, the DMA engine. You can add more logic to your memory, near to your memory, which is not possible with your DIMM factor. You can also have some administration and performance related commands by having a logic inside your CXL device, and you can program that with your PCIe kind of interface with CXL.io. Basically, we are coming up with trying to reuse some of our existing NVMe Express today, having a DMA engine to move a large chunk of data from your host memory to the expanded memory or expanded memory to the host. And you have some set of admin commands that or command set that you can program so that you can have a management protocols also managed along with it. So we can leverage some of the NVMe Express logic management and the DMA engine logics inside our NVMe Express in order to maintain the memory expansion models today. Yeah, so as I said, it comes up with PCIe compatible like CXL.io. So you also can have a hot pluggable memory. It is possible to have a hot pluggable memory similar to a hot pluggable today. What we have a NUMA node, the memory which is expanded through the CXL.mem is looked like a NUMA node, another NUMA node, and that NUMA node is a hot pluggable NUMA node. So this is conventionally this CXL.mem device is exposed to the host as a NUMA node with a specific purpose memory in the UEFI, and you can also use a scale it to a hot pluggable solution. So as it comes with the PCIe form factor, you can have U.2 or EDSFF form factors for scaling it to multiple applications. And it also supports management buses like I2C and SM bus which is similar to like PCIe device supports and useful for the management traffic. And it also can work with ACPI, Redfish, and Swordfish kind of management traffic, remote management servers. Let's talk about what is the advantage of expanding the memory over CXL. Today we have solutions with NVDIMM. If you want to have more memory, the NVDIMM model is already existing, and it have its own drawbacks when compared with CXL. So I have a table here which is showcasing the differences between NVDIMM expanded memory versus a CXL expanded memory. The form factors will be a problem with NVDIMM. It will be still a DIMM form factor. You cannot scale your form factor. With the CXL, you can have multiple form factors like UE.2, EDSFF. You can have a DMA engine closer to your memory attached. You can have a hardware virtualization enabled because it leverages the PCIe protocol. So with the DIMM form factor, you cannot have a virtualization like an SRI. We cannot be enabled on NVDIMMs. We can leverage some of the NVMe controller for the management and other DMA engine services, and which is not possible with NVDIMM. You can have a controller inside your CXL expanded memory, and you can do this block memory transfers and memory management. Everything can be done here with a processor or controller inside your close to your memory. The latencies are very low when compared with NVDIMM has a very low latency, but the latencies will, because it is beyond your system bus, the latencies were a bit low, but having a good media, storage media or a memory media, that can be actually reduced. The latency or the memory expansion model can also be reduced. So we'll talk about when we talk about the persistent memory, then we'll talk about memory expansion model and how it can reduce the the way of the compute. Today we have memory and storage model can be reduced to a single model, single memory view model, and it reduces the latencies for real-time application. So we talk about that later. So when we talk about the throughputs, the DDRs, the NVDIMMs today, or the form factors of DDRs are around 16 Gbps. But if you expand the memory over CXL, you can have a performance throughput around 64 Gbps. So the memory which is expanded over CXL, the support on the OS and UEFI side is the memory which is exposed from the CXL will use basically the PCIe configuration space. The DVSEC space in the PCIe is used to advertise the memory which is attached inside your CXL.mem. How much is the memory, what type of memory, and these all details will be shared at the time of enumeration with the DVSEC space inside your device. The host will understand the memory and type of memory at the UEFI level, and it updates it HMAT table with notifying that this is the memory which is attached to the CXL device, and it looks like a specific purpose memory. It tags it as a specific purpose memory in the HMAT table and passes this to the operating system on the host side. So with the NDCTL tools and all, we can manage this memory, and with the DAX file system, creating the direct access file system on this memory expand CXL attached devices, the applications can really use a DAX file system to see the object view on this memory, and applications can directly read and write onto these memories. So basically the applications can be modified in today's world in order to use this persistent memory model with a DAX file system. The PMDK is one of the PMDK libraries can be used by the application in order to access these devices. So in a nutshell, like on the host side, the UEFI, the Linux or the operating system will know there is a memory attached to your device and it is a specific purpose memory. And with the DAX file system, you can make this SPM memory like load store memory, and you can access that memory through the DAX file system. With the libraries in application space with the PMDK, the applications can really leverage this persistent memory. So today we have an NVDIMM ecosystem which has already been developed in order to have a persistent memory inside your DIMM form factor, and we are already using some of the persistent memory today. So the same can be leveraged to a CXL attached persistent memory, where that persistent memory will be viewed to the host application, and you can use all your PM-aware file systems, DAX file systems, and still you can use your standard API models without modifying your applications to access the CXL attached PMEM. So on the left-hand side, as I see, the NVDIMMs, or today we can call a CXL attached PMEM, can be viewed by the application like a storage, and the applications can still use read-write standard API calls in order to go into the kernel systems, and you use ext3, ext4 file systems in order to access that NVDIMM. There will be a low-level driver which breaks that access of block level file system into the byte level access. And you can also have a PM aware file system. The file system itself is aware that your low-lying device is PM persistent memory, and it will have, today we have ext3 with having a DAX file system integrated to it that can be used, and the application is not really required to modify. It can really use existing standard APIs. The file system will be aware of the persistent memory, and it will try to read and write onto the actual persistent memory. And there is a direct access mode where your CXL attached persistent memory can be visible to your host like a load store memory with a DAX file system. You can create a namespaces here. You can create an object view from the application, and do with the PMDK libraries, you can do a read write onto this CXL attached PMEM. Like a load store memory. We have talked about a memory expansion model, how the memory will be expanded and how it is getting detected on the host, and how you can access from an application this memory. And this is an expansion model. When you have added compute to it, now you are making a memory and you have a compute near to it. Basically, this will have more advantage that you can do a near memory compute. You have a memory and you want to do some analytics or functions or AI, search graphs, database engines. You can have an accelerator or a logic, a compute logic sitting closer to your memory, and it can work very closer to the memory with the low latencies. So you can half-load some of the work, like a storage engine you can implement, or a memory engine you can implement, and that logic can be closer to your CXL.mem. You can have that logic inside you, and it can do some kind of computation closer to the memory itself. So memory expansion model is used to scale your memory, and you can attach a compute to it in order to have analytical data working closer to your memory. And it also makes your persistent memory. So if you have a persistent memory, like we talk like 3D cross point or kind of memory, you will have a huge memory attached to your CXL.mem, and a terabytes of memory you can have, and huge capacity. And it is load store memory. When you applications on the host wants to access this, it is a load store memory, and it has a huge capacity. And the media of 3D cross point is actually the latency numbers will be very less. So you'll have a better performance numbers when compared with the NAND kind of storages. So you can have a memory expansion model with just memory, or you can use this as a 3D cross point memory, can also be used like a storage memory. I'll talk about in the different use cases later. But the idea here is you have a memory expansion, and you can add a compute closer to your memory also with the CXL interconnect. So disaggregated system. So till in 2019, a year back, we are talking about systems where it is tightly coupled host centric, meaning the host has different memories attached to it, and the processor have different cached levels. And for persistence, we are having over PCIe NVMe SSDs we use, and we have for persistence reasons we have storage devices. And for memory, we have tightly coupled to the processors. The memory is tightly coupled to the processors. Now with the CXL going forward from a year from now, you will see a different set of class of devices where the CXL will enable you to do a memory expansion. It is not the memory is not coupled to your host processor now. You can do a memory expansion through CXL, and you can have a compute also attached to your CXL device, and you can expand your compute from host processor compute centric. You can expand your compute to a CXL attached device. Basically, you can also have a memory and a compute expanded models with CXL. So you're distributing your compute, you're distributing your memory models with CXL. So going forward, you can see a distributed memory model, distributed compute model. And if you want more memory, you can add such CXL devices to the host. And these devices will be coherent to each other, and it can the memory and the processors inside the CXL devices can be coherent to each other when they both get connected to the host. And the memory which is inside these devices can also be looked like a system memory, and they can access each individual accelerator's memory. So this gives a different paradigm of scaling your compute and memory model. If you want more compute, you add more CXL devices which have compute capability. If you want more memory, you add more CXL devices which can be memory expansion models. So the near memory processing advantage. So we have talked about memory expansions and having a compute closer to the memory. Now we talk about real applications where this memory expansion and near memory compute models will be really useful. So if you have a memory attached to a CXL device, if it is a persistent memory, it's a storage class memory, then what happens is this persistent memory can be viewed like a load store memory to the CPU, and the CPU can access this memory like a byte addressable and cache line aligned, like a DRAM. But it has a huge capacity now because it comes with terabytes of capacity, while the DDRs are still in GBs. So if you want to have a database that has to be built, an example is in-memory database, like a Redis or Memcached. These are the cache databases where they build their databases in memory. In the DRAM, they build their databases for the faster performance, but the DRAM is limited. So if you want to expand that, they have to either expand their DRAM slots, which is very costly, and the solutions cannot be much scalable. But with the memory, with the persistent memory over the CXL, this can be viewed like a system memory, and you can build a database inside your persistent memory itself. So there are different memory models we'll talk about. How do we distribute the databases? How do we take the advantage of persistent memory and CXL today in order to scale your databases solutions today? But the intelligent storage systems today can have in-memory database expansion models and have a compute closer to it. A computational devices can be made out of it. You can have a storage engine and a memory closely coupled with CXL device, and they can work like a computational storage device itself. So these kind of models is possible with your CXL and persistent memory. So I'll talk about some of the use cases today. So with the CXL, you can have a memory expansion model, and you can have a expanded compute model. But with persistent memory, you will have, as we discussed, the persistent memory is a load store, byte accessible, right? Some of the problems today that we have with the database engines are facing is you have a memory model. In-memory databases have in-memory model where they store their databases in memory for latency purpose. For persistence purpose, they maintain the secondary storage copy. So in order to build their database, first they write into the in-memory database, and as it expands, it has to be flushed to your secondary storage in order to maintain the persistence. The persistence will give them, the secondary storage will give them a persistence and a huge capacity, but the latency, there is an added latency to this in order to access that secondary storage. So with the increased database accesses, the capacity inside your host is not sufficient to scale the performance needs. And the problem is every time you have to flush these in-memory databases to your secondary storage for persistence, and this adds up more latencies. And some of the real-time databases like MongoDB today, if you take the White Tiger storage engine, if you run a benchmarking tool, you can see the IOPS of the write IOPS will be coming down as the database is moving. As we saturate the DRAM space for the in-memory database, the IOPS coming from the client has to be disconnected in order to flush this data from the DRAM to your secondary memory or the persistent or the secondary storage for persistence. So the IOPS will drastically come down because you have to maintain these two memory models of DRAM for better latencies and storage model for your persistence. So the databases are facing the challenge of this memory model of DRAM and secondary model. If you have a persistent memory, now you have a huge capacity, low latency, and it is byte addressable like a DDR. So it has more capacity than DDR. It is byte addressable like DDR. Better latencies than the NAND or the secondary storage SSDs today what we have. So that brings a new class of memory together, and the storage, the databases can really take the advantage of this persistent memory. And if you want to really expand this memory, have a persistent memory over the CXL, and now you can have more memory, and you can distribute. If your local DRAM memory is filled up, you can expand your database into the huge capacity of your persistent memory attached to your CXL device. The latencies will be bit more when compared with the DRAM access, but still here you can create two memory models where DRAM can still work like a cache model. You can have a database inside your persistent memory with a load store, and you can have a snapshot of that also inside your DDR for better latencies. So in a given distributed memory model and in-memory databases, the persistent memory with an expansion model can be really used to expand your DRAM or in-memory requirement of having huge memory models can be expanded with CXL memory and with persistent memory attached to the CXL device. So in this way, today the Radis or Memcached, these are the one of the key value NoSQL key value store databases where a key and a value are associated with each other. The key points out to a particular value. When the request comes from the remote client, it comes with a key, and this key is hashtag to look into the hash bucket. And in this hash bucket, they look at the particular key, compare the key, and if the key is matched, the particular data pointer attached to that key is a value which is being fetched. So this is a model where your key and a value pair is earlier associated in the DRAM. Now with the memory expansion with the PMEM models, you can have a key still be in host DDR, and you can expand your value, which is mostly in megabytes, can be pointed into your persistent memory. So the memory model in expansion memory can be reutilized by rewriting some of your designs in the database to use this memory expansion model. So having a keys in your DDR and having your values inside your persistent memory expansion persistent memory. So one way, if you want a memory expansion model, use complete PMEM CXL attached PMEM as a complete memory model, build your database directly there, or you can modify your databases in order to have a key into the host DDRs and values, the huge capacity values inside your CXL attached PMEM. So this model can be utilized. And some of the other databases like Cassandra, MongoDB, which uses DRAM, a combination of DRAM and flash to organize the database. There are some latencies in order to flash this DRAM to the secondary storage for persistence. So we can eliminate this model of two memory models and have a single persistent memory model. And you can do a read write onto the persistent memory. You can build your database inside your persistent memory. You don't really require to flush your DRAM database into your secondary storage SSDs. So it reduces a lot of latencies of maintaining these two memory models. Have a persistent memory, build your database there. You have a huge capacity. You have a persistence attached to it. You don't really require to take care of other management of for persistence. So all the storage I/O bottlenecks today, we have slow media, slow storage media, and the software stack overheads coming from application till your storage media to store the actual file. These all can be eliminated with having a single memory view of PMEM and building your database directly onto the PMEM with huge capacity and persistence. And today you can also, this is a memory expansion model with PMEM, and with the compute attached to your CXL attached PMEM, basically you are doing a storage engine closer to your memory. You have a memory, PMEM memory attached to your CXL. Now you have a storage engine, so you can do a get offload or a get operations offload or set operations offload. A compute intensive task can be offloaded to your memory, and you can compute closer to your memory itself. You can build your database inside your PMEM, CXL.mem device, and you can attach your compute closer to it, and you can have a storage engines kind of thing to accelerate your IOPS. So some of the near memory compute models also is possible with PMEM and CXL. So today already some of the databases are really utilizing this PMEM model with NVDIMM solutions like Aerospike, Oracle's Xdata, SAP Sahana, Hadoop, and Redis, MongoDB. So they have different storage engines altogether, which they have designed in order to take the advantage of this persistent memory. And today they are all bottlenecked with the DIMM form factors and not being able to scale their compute closer to the memory and all. With CXL and the PMEM expanded memory models and compute models, you can have more capacity and compute models closer to your memory. Now, so this brings all together the compute models from the host centric to the memory centric, and you can expand your memory and you can take your compute closer to the memory rather than the host centric. So most of the popular databases have redesigned their databases in order to take this near memory compute advantage and PMEM advantages with persistent memory. And some of the industries already been using these popular databases are being utilizing this PMEM, and we can reuse this existing ecosystem which they have built for PMEM with PMDK and other tools in order to take the advantage over the CXL.PMEM also, CXL attached PMEM. So to the conclusion, when we come, so CXL plus persistent memory, these two technologies bring together a different compute and memory models that what we are seeing today. Every model today, what we are seeing is a host centric. Even you have a memory attached to the host, your compute is scaled towards the host. But with the new advancement in the cage coherent interconnects like CXL and the new memory models like the persistent memory, they both together can bring a new set of class of storage devices, memory devices, which can scale your compute, memory, and storage. So in a conclusion, CXL plus persistent memory is awesome. Thanks. We would like to really take your feedback. If you have any feedback about this session, please reach out to us. Thanks for attending this session. Stay safe. Thank you.